Ever wondered how AI systems learn from data so efficiently? Today, we're diving deep into the mechanics of neural networks, exploring their architecture, training processes, and the mathematical principles that make them work. This isn't just a surface-level overview. We're unpacking the core algorithms, activation functions, and optimization techniques that power modern machine learning. Let's get technical. At their core, neural networks are computational models inspired by the human brain. They consist of layers: an input layer, one or more hidden layers, and an output layer. Each layer contains nodes, or neurons, which process information through weighted connections. But how exactly do these weights determine the network's output? Let's break it down. Each neuron receives inputs, multiplies them by corresponding weights, sums the results, and applies an activation function. This function introduces nonlinearity, enabling the network to model complex patterns. Common activation functions include ReLU, sigmoid, and tanh. For instance, ReLU, rectified linear unit, outputs the input directly if positive, otherwise zero, which helps mitigate the vanishing gradient problem during training. Forward propagation is the process of passing input data through the network to generate an output. Let's formalize this. Suppose we have an input vector x, and a weight matrix W. The weighted sum for a neuron is calculated as z equals wx plus b, where b is the bias term. This sum is then passed through the activation function sigma, z, to produce the neuron's output. For example, in a simple two-layer network, the first layer computes a1 equals sigma, wx plus b1, and the second layer computes a2 equals sigma, w2 a1 plus b2. This chain of computations transforms raw input into a meaningful prediction, but the real magic happens during training. Training a neural network involves minimizing a loss function, which measures the difference between predicted and actual outputs. The most common approach is backpropagation, a method that calculates gradients of the loss with respect to each weight using the chain rule of calculus. Here is how it works. First, the network makes a prediction forward pass. Then the loss is computed. Next, gradients are propagated backward through the network, adjusting weights via gradient descent. The update rule for a weight W is W equals W, eta delta L slash delta W, where eta is the learning rate and delta L slash delta W is the gradient of the loss with respect to W. But gradient descent isn't without challenges. Issues like vanishing gradients, where gradients become too small to update weights effectively, or exploding gradients, where weights grow uncontrollably, can hinder training. Techniques like weight initialization, AG, he or Xavier initialization, and batch normalization help mitigate these problems. Beyond basic training, modern neural networks rely on advanced optimization techniques. Atom Optimizer, for instance, combines the benefits of momentum and RMS prop to adaptively adjust learning rates for each parameter. This leads to faster convergence and better performance on complex datasets. Regularization is another critical component. L2 regularization adds a penalty term to the loss function, discouraging overly complex models. Dropout, meanwhile, randomly deactivates neurons during training, forcing the network to learn redundant representations and reducing overfitting. These techniques ensure models generalize well to unseen data. Neural networks are far more than black boxes. They're sophisticated mathematical systems built on linear algebra, calculus, and optimization theory. By understanding their inner workings, you gain the tools to design, debug, and innovate in AI. Whether you're a researcher or a practitioner, mastering these concepts is key to pushing the boundaries of what's possible. If you're eager to dive deeper, check the description for links to papers, tutorials, and code repositories. Thanks for watching, stay curious, and keep exploring the frontier of machine learning. Like this video. Subscribe for more in-depth breakdowns of AI research. Until next time, keep learning.